Chapter 3, Section 2 deals with subatomic particles, which are smaller particles that are going to make up an atom. The three main types are protons, neutrons, and electrons. You're going to find the protons and neutrons here in the nucleus or center of the atom, where the electrons are going to be surrounding that nucleus in these orbitals or the electron cloud. This is a table that just relates the subatomic particle with where it is located, what size it is, and what its charge is. So electrons, again, are located outside the nucleus, and they are very, very tiny, 0.000549 AMUs, and they have a negative charge to them. Protons are found in the nucleus, and they are 1.007 AMUs, and they have a positive charge. And neutrons are also located in the nucleus. They're slightly larger than a proton at 1.009 AMUs, and they are neutral, so they do not have a charge. Now, this is one of the reasons why atomic masses are given in decimal values and not whole numbers on the periodic table, because if you were to actually get the mass of these objects, it's not just the mass of one proton. One proton is 1.007 AMUs. Same thing with neutrons. One neutron is not just one, it's 1.009. So by the time you add all of those up, you're going to have decimal values or numbers after your decimal point. This is just a little reminder on electrodes. We're going to be talking about an experiment that deals with using cathodes. So just a little background here. An anode is where electrons are going to enter a metal, so it has a positive charge to it. Opposite charges are going to attract one another, whereas like charges will repel. So the negative electrons will be attracted to that positively charged anode. The cathode is where the electrons are leaving a metal, so that's going to be where you have a negative charge coming out of. J.J. Thomson was one of the first people to come up with a model of the atom, similar to Dalton and a couple other fellows that we're going to talk about. But J.J. Thomson also came up with some information about electrons. And what he did was he figured out that electrons have mass and that they also have a negative charge. He was an English physicist, and his work dealt with cathode rays. And what he did was he shot this beam of cathode rays through this tube. Okay, that's where we're getting the cathode ray tube experiment. So the beam is being shot out, and when he put a magnet, you can see in this picture here, this is a magnet, and when he held the positive end of the magnet towards the beam, that the beam would curve up and meet it, or try to meet it, because it was being attracted to that positive end of the magnet. If you were to hold a negative end of a magnet there, it would repel the beam, and the beam would actually go away from that negative charge. So that's where he discovered that the electrons have this negative charge. He also discovered that they had mass by putting a little paddle wheel in this tube, similar to like what you might find on a paddle boat. And when the beam gets turned on, the paddle wheel gets pushed by the beam along the length of the tube. And if there is enough force behind that ray in order to move the paddle, then it must have some sort of mass. Even though it's very tiny, it has to have a mass. So that's what Thomson discovered about the electron during his cathode ray tube experiment, that it has mass and it does have a negative charge. The nucleus is the central region of the atom that has the protons and neutrons, and Thomson, same guy as the cathode ray tube experiment, came up with his model of what the atom looked like. And this was at the end of the 1800s, about 1898, and his model was called the plum pudding model. So we already have Dalton that we mentioned, and Dalton thought that the atom was a solid sphere, indivisible, indestructible particle. And Thomson kind of elaborated on that and said, well, I do believe it's this ball of matter, and I think it has positive charges with electrons embedded in the outside of it. So The majority of it makes up the nucleus that's positively charged, and then just on the outsides, embedded in the outside, are these negative electrons. And that's what he called the plum pudding model. The gold foil experiment was done by Ernest Rutherford, who was from New Zealand. And what he did was added a little bit more details on the atomic model. His experiment was with gold foil and alpha particles. Alpha particles are just positively charged particles, and what he discovered was that instead of this positively charged ball of matter with some electrons in the outside of it, that the nucleus is actually relatively small in comparison to the whole atom, but dense, and that the rest of the atom is mostly empty space. So you can see in this diagram down here that there is a piece of gold foil, similar to aluminum foil, but made of gold particles instead. And this is the alpha particle emitter, so he would turn on this alpha particles and shoot them at this gold foil, and this screen around it detected where the beams hit it. So you can see that many of the particles went straight through, and some just very little deflected, and a few, only a few, were deflected backwards. Okay, well, if there's this positively charged nucleus and you're shooting positive particles at it, well, when you hit the nucleus, those particles should bounce backwards. But if the nucleus is mostly a very small part in the middle of the atom, and the rest of the atom is mostly empty space, then that explains why most of these beams were able to go through and only be deflected a little bit, as opposed to the couple that were actually bounced back. So these ones that were shot backwards probably ran right into the nucleus, whereas the rest of these made it through the other space in the atom. This diagram here is just a cross section of that, so you can see when you actually run right into that nucleus, it would cause the alpha particle to go backwards. But if you went through a different part of the atom, then it would still allow that ray to pass through. Atomic number, as I mentioned, is how many protons are in the nucleus of an atom. When you're looking at mass number, again, that's the total number of protons and neutrons in the nucleus. So if you're given a symbol such as this one here, this is called a nuclear symbol, where you have the mass number on the top, the atomic number on the bottom, and the letter symbol next to it, you should be able to tell me that the mass number is 4 here, that the atomic number is 2, and then you should be able to identify how many protons, neutrons, and electrons that this element would have. So for this particular isotope of helium, 2 is the atomic number, so you automatically know that there are 2 protons. And 4 is the mass number, so if mass is protons and neutrons added together, well, then we can decipher that we will only have 2 neutrons. And then at this point, electrons are always going to be equal to protons. Unless we see some sort of charge here, positive or negative, then that means that our protons and our electrons must be equal to have neutralized one another. So our electrons in this case would also be 2. Coulomb's law tells us that the closer 2 charges come together, the greater the force is between them. And again, opposites will attract and like charges will repel. So essentially, if you decrease the distance between 2 objects by half, you're going to quadruple the force between them. This might have been something that you thought of before, or maybe you hadn't thought about it yet, but protons are all positive, and they're all located very close together in the nucleus. So if like charges are going to repel each other, then how do they stay close together in that nucleus? And the answer is the strong force. A strong force is actually greater than any repulsive force when you get at a close distance. So at some point, as protons are coming closer together, they will want to repel, but eventually they're going to reach a point where they're close enough that this strong force will take over, and it will actually allow them to stay tight and compact in that nucleus. Finally, isotopes are just atoms of the same element that have different numbers of neutrons. So for instance, helium here we can write it as helium-3 or helium-4. It has two different isotopes. Whenever you see the word written out with a hyphen and a number after it, that number is its mass number. So helium, if you look on the periodic table, has an atomic number of 2. So that means that it will have 2 protons. So if this is the mass number of 3, then we could also decipher that there would only be 1 neutron in this type of helium. As for electrons, we know that there would also be 2 electrons because they would be equivalent to the protons. In this isotope of helium, helium-4, again, we know that helium's atomic number is 2, so it has 2 protons and 2 electrons. But in this case, with a mass number of 4, we're also going to have 2 neutrons. And finally, radioisotopes. They are isotopes that are unstable and can undergo radioactive decay. You might have heard of half-lives before. A half-life is how much time it takes for half of the material to decay. And various materials have different half-lives, ranging from seconds all the way to years. So it's just going to be how fast that isotope can actually decay. And that is a radioisotope, an unstable atom.